I am Hui Huo Zheng. I'm from Argonne National Lab. Another role that I play is MLPerf Storage Working Group co-chair. I'm one of the 3 co-chairs. Today, I'm going to talk about our efforts in benchmarking storage for AI. The title says Beyond Throughput, Benchmarking Storage for the Complex I/O Patterns of AI and MLPerf Storage and DLIO. This title is generated by ChatGPT. I provide all the context, figure out what is the best title, and I think it gave me a very satisfactory answer. Particularly, I like this Beyond Throughput. I came from the HPC environment initially, and what we care about is the throughput, right? Even compute is the float number. I/O is the bandwidth or I/O ops that we can get. But when we step into the world of AI, we found that this metrics kind of like not that good anymore. And you will see more and more later on in talk. And just a little bit information about the Argonne National Lab. And I am from the Argonne Leadership Computing Facility. Many of you may heard about the Aurora, which is one of the 3 exascale computing systems. It has 60,000 Intel PVC GPUs. And what is more related to this audience is the storage system that we have is the DLIO, it's short term for Distributed Asynchronous Object Store System. And the capacity of that is about 200 petabyte. And then the theoretical peak that we aim at is 30 terabyte per second. It includes 1,000 DLIO server. But so far, we only have like 200 set it up for the user. In later November this year, I believe that we will have the whole system set it up. And besides Aurora, we also have an NVIDIA machine called Polaris, which contains 2,000 NVIDIA A100 GPU. And we also have a lot of some smaller, kind of more advanced NVIDIA GPU system for our testbed. And besides that, we also have quite a few AI testbeds. Argonne is assigned by DOE to kind of lead the effort of AI. So we have Cerebral, Salmonova, GraphCore, and GraphRag. And we are constantly kind of looking for new AI testbeds. And basically, the facility is a way we provide these computing resources for scientists, for and faculty members in the university. They can apply our allocation program, and they can use our machine for free. This is a purely open for open science. And my another role is the co-chair of the MLPerf Storage Working Group. And this, I believe, if I remember correctly, it started in 2021. But when I joined, it was already kind of 1 year after it started. I wasn't aware of the storage benchmarking effort. I have been doing the storage benchmarking. I developed the DLIO code, which I will talk later on. And then my manager figured out this effort and then asked me to join. And then since then, I joined. And then later on, the DLIO became one of the kind of back-end software for this benchmarking effort. I put a lot of logo here. I don't know whether include everybody here. If you are not there, make sure to follow the link, join our working group. If you are already there but not on this slide, talk to me afterwards. We constantly have new members joining, and this working group is growing. Even the number of submitters you will see later on grow a lot in the past few years. And so today, what I'm going to talk about is, first, I will start with overall view, on the top level view, like what is the interesting thing of storage in I/O, particularly in the context of AI. And also probably has a little bit flavor on the HPC environment or in the DOE, Department of Energy space, or AI for science space. And then I will talk about how we designed this DLIO and later on included in this MLPerf storage community benchmarking efforts and some lessons we learned. And the lessons I learned will be a little bit more technical. I was told, this is my first time joining this conference, and the organizer told me that this is a very technical conference. So make sure talk about technical things, not just the higher level things. So then I provide some technical things. Hopefully you like it. In Argonne or in the DOE space, we have this allocation program called Insight. I have also another program called ALCC. And this other allocation program that university professor or scientists apply for our resources. And they submit a proposal, and if their proposal is good, their software is ready for using the HPC system, they will be awarded. And this is the percentage of the AI among all those proposals. Basically, those proposals, whichever has the AI component divided by the overall submission, and you can see a growth across the year, right? And basically, it started in 2017. And that is the year kind of deep learning become more and more popular in the science space. I remember I attended the American Physical Society annual meeting. I was a physics postdoc during that time at the Argonne National Lab. And then I found out that those AI kind of room are fully packed. Even the hallway are packed. But those traditional like material science simulations, density functional theory are kind of not too many people. Now at that time I know that AI is kind of gradually growing up, right? But many scientists at Argonne are still kind of skeptical whether this really work or not until maybe large language model comes up. And that's in the time frame of 2022, 2023, and we start to catch up. And this, you can see the allocation kind of grow, kind of very deep, right? And so now, this year, we have almost close to 50% of the proposals submitted have AI component. And I would say majority of them are kind of having the large language model component in it and beyond traditional deep learning application. And of course, to consider the need of the storage for AI, I think two things. On the capacity side, you just see the amount of data set, right? The largest one on the top is beyond 100 terabyte of data set. And 100 terabyte is a kind of like a default capacity we give out to the project, 100 terabyte. Smaller project only get 10 terabyte of capacity allocation in our storage system. And so we consider 100 terabyte, more than 100 terabyte is a kind of large storage space. And not only that, also the checkpointing require a lot of storage space. And actually, I was doing this MLPerf storage submission, and I was running the 1T model checkpointing, and then it kept failing because later on I realized that it was because the project that I got allocated doesn't have enough capacity. I was only like 100 terabyte of the space, but this one checkpointing is 18 terabyte. So if I run the 10 checkpointing already beyond 100 terabyte, right? So then I realized, wow, even myself didn't get the change or the mindset, storage, even the capacity of the AI need is really growing, right? Traditional scientific simulation doesn't need like 100 terabyte of data for single workload, but AI does need. And and also, throughout the year, I learned that this AI has new kind of AI I/O patterns. If you consider the HPC workload, they are typically write-intensive, like molecular dynamic simulations, climate modeling. You have huge amount of checkpointing data, and it's primarily write. The read only happens when you read the input or when you want to restart the calculations, right? And also it's bulk parallel I/O using MPR-IO or HDF5 library built-in. And the data is multi-dimensional array, which is very simple and trivial in a sense. And it's single-threaded, synchronous I/O. And even though our storage system, HPC system, were equipped with non-local storage, we very rarely see HPC workload using those non-local storage. Because the HPC people, workload people, they don't want to deal with this moving the data on their own, and then it's just not really useful. We do see one or two workloads using that, but not as frequently being used as AI workload. And now you consider AI workload, especially in the beginning of the deep learning transformation, is really read intensive, right? You need to read huge amount of data, and then you have a lot of small and sparse I/O, metadata intensive, and also the data format is kind of very variety format like JSON, text, key value format, and then it's also multi-threaded, asynchronous I/O, right? This is the kind of one of the important feature of the Python workloads. And then storage hierarchy become more and more important. And you will also see something later on in my slides. And also this kind of huge pipelining include different kind of stage, including data preparations, pre-processing, data loading, checkpointing, even inferencing. They have kind of different I/O need. Not like traditional HPC, you just meet the need of the checkpointing, then it's okay. But then for the AI, different stage, they have different requirement. So, and then I think in 2017, I take some time to scan through all the popular AI workloads in commercial AI workload, and also in the scientific domains, particularly 3D Unite ImageNet is kind of two popular ML common training, MLPerf training workload, and Cosmoflow and DeepCam are in the MLPerf HPC coming from the lab, FFM, and then later on the large language training. And this is the kind of overall view about the domains and the sample size. You can see it range from the 100 kilobyte to like 100 megabyte. And it's stored in different kind of format. And the total size of the data set also range quite a lot. And in terms of the I/O stress pattern, some are kind of metadata intensive, some are kind of bandwidth bounded. And some include random reads, etc. Right? So it's huge kind of in a landscape. And basically, I think we need a storage benchmark. And we need a benchmark to really understand the access pattern of AI workloads. And easy for us to identify the bottleneck and propose optimization. Right? Running the full workload is just kind of too tedious and too complex. But we need a simple benchmark, allow us to simulate different kind of setup, and then we can inform the researchers or practitioners the best storage solution, and also guide the storage and AI software and hardware co-design, right? So hardware need to improve, and many times it was the poor kind of design of the software give a lot of pain to the hardware, right? So it's really a co-design process. And benchmark, I think in this community, probably FIO is familiar to everybody here, right? It is a very good tool on the single node level. In HPC domain, we have the IOR, which is kind of simulating the checkpointing with different kind of block size, I/O patterns, and in the HPC domain. And when we consider, do we need to develop a new benchmark suite for AI? And the answer is yes, because these are kind of focused more on the HPC or traditional workload. It doesn't have the multi-threaded, doesn't have the asynchronous I/O, and then also it's too low level. We need a kind of a benchmark which kind of familiar to the AI practitioners, which can be configured at higher level, and you will see later on. And this we start to design this DLIO benchmark. And if we consider this, the whole kind of pipelining of the AI training, it includes the data preparation, and then store in the storage system, load it into the CPU host, and then transfer to the GPU for training. Of course, during those times, when we start to consider this benchmark, GPU-initiated I/O requests still not so popular yet. GPU direct storage was there, but we found that people doesn't want to use GPU direct for two reasons. One is that loading the data to GPU, then you didn't have the overlap of the I/O with the compute, right? Because the GPU need to wait for the data to be loaded to GPU. Second thing is that in a lot of training, it involves the pre-processing of the data, right? And that part is compute. And if we load it to the host, then host can participate in this compute, and that part of compute can also be overlapped with the compute in the GPU. So that's why kind of not too many people think about using the GPU direct. But now later on, more and more kind of people start to think about the GPU initiated I/O request. And so then we figure out, okay, if I want to have this kind of DLIO, how about I just maintain everything, but just take away the compute or replace the compute with a sleep statement. I maintain the same kind of data loader so that it looks like an AI kind of software, but all the compute is replaced by the sleep statement with the same amount of time. And with this, we get the advantage of we don't need this actual accelerator to run the benchmark. And this is a huge, huge win because many storage vendor doesn't want to kind of set up a GPU system to run our benchmark. We just need a bunch of CPU hosts and then connect it to a storage system, and then you can run a benchmark, right? So I think that's probably one of the major reasons this easier for the storage vendor to submit the result. And second thing, as I mentioned, we use the framework data loader. The real workload use PyTorch data loader. We also use PyTorch data loader, TensorFlow data loader, and all the configuration there is the same. Number of workers and prefetching, etc. Everything is the same. And then we also find out we need to support data generation. And in a way that people doesn't have to download the huge amount of data set from internet and then do the benchmark. We generate the data as long as we configure like what is the sample size, how would you want to kind of store the data set, how many sample profile, etc. All those configuration. And then we want to make it configurable to different workload. We want to have a single core, but just by tuning different parameters that you can simulate different AI workload. You can simulate the LLM checkpointing, you can simulate the unit 3D or Cosmos flow without the change of the code. Just do the configuration. And so we have this modular design, and we configure the workload through a YAML configuration file. And then we have the benchmark runner. Benchmark runner also call the read for reading the data, and then write for doing the checkpointing. And this can be connected to different kind of storage. You just need to add a layer. It can connect to S3 or POSIX file system. And then we have the data generation module also. And then the other important thing is we need a holistic performance monitoring and tracing across all software stack. So the important thing to me for the benchmarking is that we need to know all the detail, like different level, whether it performs well or not, so that we can know if there's a poor performance, whether it's due to the software or due to the storage system, right? And then so that we can know how to optimize. And then this is an example of the configuration file. And you can see if you are the AI practitioner, you know that the YAML file really looks like the real workload, right? We have the model setup, just tell the system what's the size of the model, which framework is using, and if you're doing training or data generation, and in terms of the data set, where do you want to put the data, which format, number of samples, etc., right? And then in the reader, we also set number of worker, batch size, which data load are you using, those kind of things, right? And then how many people you want to run a benchmark. So it looks like hourly, just like running a real AI workload, right? Except that the computational time now is simulated as a sleeping, right? We just doing nothing there, waiting for the data to be ready. And then this is a checkpointing workload. We also can define number of layers, number of KV heads, what kind of parallelism we are doing, pipeline parallelism, data parallelism, etc. And how many checkpointing do you want to write? Now, I will start with give you some confidence that this benchmark tool actually generate the similar I/O pattern of the real workload. So I compare with the Unit 3D, and I will mention a little bit more about this is the tool that I mentioned for the monitoring or profiling and tracing. I will mention more later on. And you compare with the real workload and the DLIO workload, right? So here you can see this is a multiple worker doing the I/O loading. The main thread is the first row and doing compute. In the DLIO is doing kind of sleep. And the I/O thread are doing loading the data. And you compare the pattern is essentially the same, right? And you also see that, okay, in the beginning, they are prefetching. So in the prefetching stage, almost every worker reach out to the storage system, right? So prefetching is a very intensive period of phase. And that's why in your AI training, the first time step take much longer, right? For two reasons. One is if you have a GPU, initialization of the GPU training is longer, but a lot of time also this multiple thread accessing the storage system take it longer. And then later on, you can also see that it's loading data whenever one batch of data get consumed, it will try to load new data, right? And if I do it schematically, basically the main thread is doing training, the I/O thread is doing the data loading. And if the data loading is not fast enough, there will be a store in or idle in the compute time, right? So we define the metrics basically is the accelerator utilization. If your I/O is very fast, because it can be doing things under the hood, then your GPU is always busy. You get a 100% utilization, right? If the I/O is slow, then constantly GPU has to wait for the storage system to feed the data, then accelerator utilization will be very low. We also have another throughput, just number of sample per second, right? See how fast you can load the data. And so this is the overall benchmark metrics we use in the MLPerf storage benchmarking effort. Now I want to say a little bit more on the I/O profiling and tracing for AI. So this is for monitoring the I/O performance. I don't know, for those who know the Chinese, you can read that. Basically, it's like in Chinese, all the doctor try to understand the whole things, right? Maybe the Western way, If you get a pain in your finger, you try to fix your finger, but in China, it would link the symptom to the actual problem inside, right? To have full diagnosis. And this is the tracing tool. Eventually, we know that there are a lot of existing tools like Dashian Profiler Recorder and some kind of Linux system use IOProf, but they are kind of just profile the IO level, right? You get a lot of trace of the IO access pattern, but does not link back to the actual application. And so we need a profiler with very easy to use, just plug in, set the environment variable, and then generate a trace result and visualize it. Second, it works with Python application. I found that all this profiler doesn't work well with Python. It only provides a trace for the main thread, but Python has a lot of background thread doing the I/O. And I found out that none of those in the beginning. Right now, they all improve, try to kind of adopt the AI workload. When the first time I used this, none of those generate a trace for the Python workload. And then also, we want to profile at different level. Once you see the trace, you will see what do I mean by different level, right? And easy to integrate with other tool. Of course, it should also have a very small overhead. And you can check the paper. And so there's a whole tool called DF Tracer, and this is built into the DLIO core also. And this is the tool. Eventually, how to use is that we have just import the library and then decorate the specific function, particularly because we are interested in the data loader. So I will decorate the pre-processing part, read the data part, and get item part. And this below is the trace that I got. And you can see that it contains all the level. The main thread is doing the training, and then doing the training, it also contains the compute, host to device transfer. Then you can see the get item is where each sample is loaded, right? And then going to the get item, you see is doing the posit read. So now this posit read is actually linked back to the Python get item code, right? And this is very useful, as you will see later on. And there's also providing information, seeing that which code, how expensive they are. And the first thing I found out is that because we have this holistic view, the first thing I tried before is I just compared the PyTorch and TensorFlow, and I was using HDF5 format. And I immediately found out that, interesting in PyTorch, you can have different workers loading the HDF5 file, whereas TensorFlow, you cannot because of the thread locking, thread safety. So you can see all the posit read are all kind of stay away each other, right, from each other. It cannot do multiple read concurrently, but PyTorch can. So that's why PyTorch with HDF5 work well, because PyTorch created workers with processes, but TensorFlow is with thread, right? So this kind of information can be easily seen with this DF tracer. And so whatever I mentioned is the tool side, right? And the MLPerf Storage Working Group is to kind of define what are the workloads that we want to focus on, and then what are the rules for the submissions, and etc. So the things listed here is the round of submission we just finished. We have 3 round of submission already, and this 2.0 is the most recent one, and the result was released in August. And we have 3 training workloads, UNet 3D or 3D UNet, ResNet 50, and Cosmos Flow. And we are gradually incorporating new other kind of more recent workloads. And we also added the checkpointing workload. And specifically, I think if you attended Wes' talk earlier, we have from the smaller one, AB all the way to 1 trillion parameters. This is a summary from the early time. We have the 0.5. We have 5 organizations submitted the result. But now you can see we have 26 organizations submit the result. It grew quite a lot, right? I think David Conter is in the back. He can say that this is the number one kind of in terms of the number of submitters, right? Almost.
So, David from one of the founders of MLPerf, and so the MLPerf Storage Working Group set a record for the number of submitters, but unfortunately, you guys were beat just last week by MLPerf Inference by 1.
Oh, okay.
What that means, though, is we have a competition. So you're benchmarking the benchmarkers. So if you're here and you are interested in it,
Yeah.
performance, you should get involved in
Yeah.
storage so that they can retake the crown from their
Right. So make sure all of you get signed up to the working group and participate in the submission also. Right? And then if you want to know a little bit more detail, what are the different kind of storage type that make the submission, you can check the link for more detail. And so it's a wonderful thing to me to have a community effort because we want to kind of really explore the whole landscape. We want to explore different kind of storage solution, right? IBM Spectrum, Lustre, Deos, or cloud storage, or a lot of kind of new NVMe drive, and different kind of storage solution, and see how it performs for different type of workload, right? And this can only be done with a community effort, right? At Argonne, we only have Lustre and Deos, and I can only know to a sub area of the landscape, right? But with all of us participating, we can get the whole picture, right? And also, in terms of the software, we have data loader. We can use a lot of data loader and many kind of other technology, even data format will play an important role here. So it's a wonderful thing that we can all participate so that we can get a kind of better understanding of this AI thing. Now I would like to go a little bit more on the technical details, the lessons learned from these MLPerf storage submissions. And I will start with the Unit 3D workload. And this is the pattern. And so when I try to kind of find out the best configuration for a best setup for the I/O, best I/O, I usually start with the number of worker 1 so that I can get out the compute and I/O ratio, right? In Unit 3D, it's an I/O intensive workload. You have like 100 to 150 kind of megabyte per sample, and this is kind of big on the big range. And so you can see here the compute part, which is the here is the compute, and this is the loading one batch of the data, which contains 7 samples. And because of and this is tested with the NVMe drive, and you can see because of the I/O is not fast enough, the GPU was idle here. And so the I/O is more costly compared to compute. It's 1.3, right? But the good thing is that we can always spawn more threads to do the I/O. And because it's 1.3, we can know if I increase the number of workers to 2, I should be able to cover the cost, right? So then increase to 2, you can see all the idle time was away, right? So now we can meet the need, and the AU immediately increased close to 100%. And going a little bit closer, I also find out that even though I'm reading one MPZ sample, but surprisingly, under the hood, it decomposed to a bunch of POSIX core, and each of the POSIX core is 256 kilobytes, and which I immediately figure out that probably not good kind of performance. So I just switched to HDF5. I know that HDF5, when you read the data, it will read the whole thing. So the transfer size will be like the size of the file. Instead of loading that by small chunks, it will load in the entire file. And because of that, immediately we found out even with number of workers equal to 1, you compare with HDF5 and MPZ, HDF5 is faster, right? So I only need one thread to do the I/O now. I don't need 2 threads. So I increase the I/O. This is the same data, but just stored in a different format, right? So you can see that this is not too much of the storage performance, but it's actually the software part, how you organize the data, right? And of course, previously it was with A100, but now with H100, the compute is much faster. So it's 2 times faster. And what we did is just increase the number of workers, right? Still can meet the need. So with MPZ, we use the number of workers equal to 4. With HDL5, I think this should be 2. We can still meet the need. And now, earlier it was doing things with NVMe. Now I also try with the Lustre. And now we find the similar story, but now the Lustre, the chunk size is actually 4 megabytes. Previously it's 256 kilobytes. I haven't kind of checked in detail how the NumPy array data loading library deal with different type of systems and make that difference, right? But it's kind of interesting thing to know that different storage will impact how the software load the data. And important thing I know also when I was playing with the MLPerf storage submission algorithm system is that if we increase the number of GPU on a node, the bandwidth need increase linearly, right? So in particular for fast accelerator, if I do like A, I need 23 of a gigabyte per second of data to feed to meet the need of 8, right? So this, you will find out that if you are doing a local drive, you have to use probably multiple NVMe and then have multiple PCIe link to be able to feed that amount of kind of data fast enough to support the need of the 8, right? If you are doing remote, then probably the NIC is important. Number of NIC is important, right? So when I was testing our algorithm system, I figured out that the system that I tested doesn't provide enough kind of number of NIC. The NIC become a bottleneck for me to transfer the data inside the compute node. Another thing, as I mentioned, you see that NumPy array and HDL5 has different kind of overheads, right? So even though you may track your NVMe, theoretically you may be able to provide 10 gigabytes per second, but when you load that with the NumPy array, you probably cannot get 10 gigabytes per second because of the software overhead. So that also need to be considered. And besides that, when you scale out, you'll find out that actually it can also be bound by the overall kind of peak bandwidth of the parallel file system. In this case, I was testing the Lustre file system, which the peak bandwidth is 650 gigabytes per second. And as you can see, as I scale the number of nodes, it was bounded. But if I place the data to NVMe local drive, I can keep scaling linearly, right? So that's important thing to know. Also, NVMe is still important in bringing the data close to compute. And these are the kind of similar analysis to other 2 workloads, which are a little bit less I/O intensive. I'll just skip the main result. ResNet 50 also, probably you all kind of now know that many small files doesn't perform well, right? We learned that in the Lustre file system, when people are doing with millions of files, always cuts the Lustre file system down or kind of get stuck. Even you cannot do ls commands quickly, right? So, and not only that, you also find out that actually if you store the file as a PNG file, the actual I/O code, there's a lot of software overhead of loading that image, right? The actual POSIX code is just a small fraction of the overall get item. And then with TF record, it solves this, not just reducing the number of files, but even the software overhead is reducing. Then I quickly go through, besides the traditional training workload, we also have large language models. And in large language models, the entire pipelining is that we download the data, pre-processing. In this particular case, pre-processing involves mostly like a tokenization. Besides the deduplication, it's actually tokenization. And once we tokenize the data, we store the tokens in a binary file, and this is what MapTranDB is doing. And then we memory map of the binary file and provide it to the data loader and do the training. And then we store the data back. And it's important to know that what are the needs of the different stage of this pipelining. I'll quickly go through. First is on the tokenization side. Tokenization, we just load the raw data, and then tokenize it, and then store it back to the binary file. And you can see the same trace file tell us that the read part is very minimal over here. Majority of the thing is in the compute. And then sometimes, once in a while, you need to read a kind of 4 megabyte of buffer to the binary index file. And we also know that it's roughly like 2 megabytes per second per thread. So in a single node, if you have like 32 CPU core, you can get about like 50, 60 megabytes per second, right? So because majority of the time you are spending on compute. That means actually I don't need to actually download all the data. I can do streaming. I can do streaming, and while I'm streaming the data, I do the tokenization, right? I can eliminate the need of the storage for storing all those raw data. The other thing, I mean, many people say that, okay, this read part is not it is a small overhead. The training part, loading the data, is very cheap, right? And we use the profiler, we can actually see that. And it's loading that one batch, mini batch of data is in a millisecond range, whereas the training step is like in a 10-second or 1 minute range, right? So this is not IO intensive. So majority of the interesting part is on the checkpointing for the large language model. In checkpointing, people use sharding because of the different parallelism, right? And particularly related to the checkpointing data, it matters a lot whether we are doing pipelining parallelism or doing 0-3. So the first case is that in writing the checkpointing data, there are primarily two types of data. One is the model part. The other is the optimizer part. And optimizer contains maybe more than 80% of the data is optimizer data. And so in the first scenario, where we have pipeline parallelism and we use 0-1, the optimizer is sharded across all the GPU. But the model is sharded only within the data parallel instance. That means that they are redundant across the different data parallel instance. So then when you write the checkpointing, basically the optimizer part is every rank write their own kind of data that belong to it. But the model part, only a part, the first data parallel instance will write the model. And that's the entire model, right? Whereas when you do 0-3, and this is, we sharded everything. We sharded the model and sharded the optimizer. And typically, for smaller model, we use 0-3. For bigger model, like 4 or 5B, we do 0-1. And this also have impact on the scaling performance. The plot shown here, as I was doing testing while I'm submitting the 2.0 storage benchmark submission, I do a scaling test but on Dell's file system. At that time, we have about 200 server, and then you can see different model size. On the 1T model, eventually I was able to write the entire 18 terabyte of data within less than 5 seconds. And the bandwidth that I achieved close to 3 terabytes per second. And also for other storage, other model, as I scale, you can see the bandwidth is also increasing. But then there's some kind of penalty here. The penalty is because of the two reasons that I mentioned. Let me just quickly go through this. This is the actual I/O pattern for the thread pointing. We want to see, like, in the thread pointing, how much data we actually write it out in terms of the transfer size, right? So you can see the model part is, because it's smaller and then gets shorted, this is with 0.3, you can see that the transfer size is pretty small. And if I increase more data per hour instance, this will become smaller and smaller and eventually become a bottleneck. Versus the optimizer, those are big chunk of data, like 4 gigabytes. If you continue to scale data per hour instances, this will continue to scale. And this is what we found here. If I scale to large scale, the optimizer part linearly decrease, but then the model part eventually become a bottleneck, cannot scale anymore, right? But eventually, of course, in this case, I still kind of can write the whole data thread pointing less than 1 second. Another thing for the bigger model, 1 trillion, as I mentioned, only the first data per hour instances write the model part. The thread pointing, the optimizer part, everybody is writing it. And eventually you can see, because of that, it also become dominant at large scale. Because the model part, just the same number of GPU writing the data, and it takes same amount of time. But the optimizer part will keep decreasing, right? So that's what we learned, right? And now, kind of, in terms of the order of magnitude, we can all finish all this thread pointing in less than 10 seconds. And usually training, when Argonne kind of, after the acceptance, people start to use our system. In the beginning, when we are testing, the system was not stable. So almost like every 15 to 30 minutes, we have a node failure, like pin failure. So we really need fast thread pointing. And it's good that, at least for the AI model training, we can finish this in less than 10 seconds for this model thread pointing, right? So it can provide all the need. And future, this is the future roadmap of the MLPerf Storage Benchmarking Group. We want to incorporate new workloads, including like graph neural network and other kind of model that potentially have interesting I/O pattern. And KV cache now become more and more popular and important, and vector database. And then now also the GPU initialized data loading, right? And because we see more and more, if we need a lot of kind of bandwidth to drive the data loading from the storage to the GPU, sometimes the host is not powerful enough to make that data movement. We need the GPU to spawn more threads to drive the data movement. A takeaway, that AI really changed the storage game, right? It's no longer just purely focused on the bandwidth, but we have to look at the whole things. The access pattern are different, and then the whole software stack will impact the overall throughput things. And benchmark is important, right? With this benchmark tool, we can quickly identify the bottleneck and then play with different kind of setup and now feed back to the actual application. And also we can find out now, for example, the NumPy array is not good, and we can inform back to the AI community. Either you need to improve the NumPy array library or switch to other library. And it's nice that we can have a community to work together to explore all these things together. With that, I would like to thank the support from Argonne and all the people who participate in developing the benchmark and define all the rules for the submission, etc., including the people at Argonne and the MLPerf Storage Working Group. Okay, and I can take some questions. We are working on that. Yeah, the RAG part is the vector database. We are working on that. We have a sub-working group. So if you are interested, join join the main working group, and then we will assign you to the sub-working group to develop that. Mm-hmm. Any other questions? If not, thank you very much, and you can talk to me.